Hi, and thanks for tuning in to the CBA Podcast, a place where we chat about our own recent achievements in the area of electronics, software and mechanical engineering, and more likely than not, give excuses for not having done anything at all. Hello, and welcome back to another CBA Podcast episode. First of all, the sound that you may hear in the background is the air conditioning. Air conditioning is gonna be on all the time. I hope Audacity filters some of it or all of it out. If not, too bad. But that's how it is. You're probably aware that right now, at the time of recording, there's a global pandemic, a coronavirus pandemic, start of 2020. I'm not going to talk about that a whole lot. I guess you heard it all. The media is full of it, so I'm not going to do that. But I'm going to say some things that keep me busy. To be honest, my work and my hobbies are pretty much me by myself, so not a whole lot changed, but some things that I do to keep myself busy is getting to know my equipment, my electronics equipment. So I think it's always good to get a better feel for what it can do and what its limits are. I'm going to talk about this a little bit later on, but for example, I've been using the second-hand spectrum analyzer that I got a long time ago a little bit more. I've been doing some standing wave experiments with a coax cable. That may be nice for you as well, I don't know. Some other stuff that I might be doing in the near future is taking apart some stuff, because I always like that. There's always a surprise, and you learn something and it cleans up quite nicely. You toss the stuff in the bin afterwards. And here's a message from me to you, boys and girls. Don't take apart 5G cell towers. You know, I reckon it's about 1 hour if you do proper preparation and a getaway route, and it also costs fuel and matches and so on. So how about get a nice cup of coffee, a nice cup of tea, whatever you want, and you sit down for that hour and you read about RF radiation effects on health, and reconsider, please, because I think it's a bit silly. It seems to be a trend right now, destroying cell towers. I hope it's quite short, because this sounds like Middle Ages. But whatever. Some other stuff that keeps me busy, or makes me happy in this time, is realizing that the virus has little to no impact on a lot of nature. So trees and animals are still doing the same stuff they have been doing for a long time, and it's always there. Sunrise is always there, so it always looks nice. And depending on where you live, if you look outside, it's pretty much still the same, I guess. At least here. Some other stuff that I do is listen to podcasts. Now I realize some podcasts, no, pretty much all podcasts I listen to, I do so because other people have pointed me to them. So I'm gonna, in the show notes, include some podcasts that I listen to that may or may not have to do with tech at all. But it's quite relaxing, so at least it gets your mind off the stuff for a few hours. And last but not least, definitely, is the upcoming Retro Challenge. The Retro Challenge is a online competition to do something with old gear, basically. Old hardware or software, or something in the spirit of old hardware and software. So the idea was to do that twice a year. John Linville hosted that for a time, and I think before that someone else, and before that maybe someone else, but I don't know his or her name. And Michael Mulhern helped with hosting for some time, and now Mark Sherman has taken over, apparently, because there was a problem with getting judgment results out on time. I don't know, but it's not a big deal. But I hope it will continue. The ongoing Retro Challenge is started right now, start of April. I may compete, but no idea. It's a friendly competition, so there's not a whole lot of actual competition going on, but it's more like a fun thing to do together and see what other people are up to. And the current competition lasts to the end of May, so I'll surely put a link to that in the show notes. I'm not sure if I'm going to do anything, because it is a commitment. But if you're searching for a project to do in the meanwhile, and you're going insane or something like that, then maybe this is for you. Oh, and also, there's not going to be any events at the end of the podcast, upcoming events, because I think all live events will be cancelled anyway for some time. So if you're looking for that, too bad. Instead, I'm going to talk a little bit about stuff that I made since the last episode aired. First thing is a very big, very simple mains test-jig. and it's not very complicated. It has a input fuse, that's what I wanted, 1 amp or even 500 milliamp fuse, I'm not really sure right now. Switch, you can turn on your device. It has a socket where you can plug your mains device into the test-jig, and also it has a timer, an interval timer. You can control the on and off times and have your mains device turned on and off automatically. So for example, if you want to test if your mains device can withstand being turned on and off 1000 times, you just configure this thing, turn it on, do something else and come back and see if it still works. Or if you want to measure inrush current, you can do that. Instead of just turning it on and off by yourself, you can use this. It has a few relays. You can also use it for some other stuff, but that's basically what it is: a fuse, a switch, and an interval timer. Now this thing is ridiculously huge. I talked about making test jigs out of DIN rail components earlier already in a few episodes, I think, and this is also made out of DIN rail components. It has a DIN rail stuck to a big block of wood to give it some weight, and a few cable ducts around the front and cables, and that's basically it. And it connects to mains, and the mains device connects to it. I'll put a picture of that in the show notes. Now, DIN rail stuff is very nice to make test setups, I think. It has some downsides, but the biggest advantage, I think, is that it's really fast to make. You can use it like Lego or even Duplo. You can quickly click together your test system, or even permanent system, but I only use this for test stuff, basically. Obviously, the downside is that it's costly. I find that DIN rail components, for example, power supplies and relays and switches and lights and terminal blocks, are ridiculously expensive if you really look at what they do. But of course they have to be robust and foolproof and safe. Be safe in hazardous conditions, so that's probably why they cost so much. Now, once you have that stuff, it's not a big deal, because you can, at least for me, what I do with it, building test setups, is you can make your test setup, do your test, and afterwards just disassemble it and retrieve your modules, your DIN rail modules, and toss all the wiring and the cable duct and the rest away. And so you do an initial investment of buying the modules that you need, switches and power supplies and sockets and terminal blocks and stuff like that, relays, and then reuse them over and over and over again. I did it a couple of times already. It worked quite well. And you end up having a very safe and very clear device. So, but it's big, as I already said. If you look at this, it's I'll put a picture of this in the show notes. It's probably 40 centimeters wide, and if you look at it, you probably think, hey, I can do the same with 5 centimeters of breadboard and a few relays and a few switches, and that's true, but this is easier and safer and more robust, I guess. And here's a semi-related thing having to do with test jigs. Now, you don't have this problem with DIN rail stuff, because you can replace everything on a DIN rail, basically, with a new part. But I found myself recently replacing a 30-pitch connector or something like that on a PCB that had worn out because of use, and it was indeed part of a test jig. Now, this connector has been mated with a part to be tested for thousands and thousands of times, so eventually you don't always have the most gentle people operating a device, and eventually mechanical stuff breaks down. So lesson learned for me is make the mechanical stuff that wears out replaceable. So don't integrate it directly on your PCB. Make a adapter board or an adapter cable or something that you can then replace. So that's what I learned here, the hard way, I guess. Right, so another thing that I made, and I'm sure I talked about this in a previous episode already, is a digital driver box. And what this thing does is take, for example, CMOS signal or 3.3 volt signal, digital signal, and convert it to a higher voltage and to a lower output impedance. So you can, for example, use a signal coming from your signal generator and use it to drive a serious load or even a motor or something like that. And you can use PWM signals to actually drive some load. And I use this, for example, as open drain output to drive LED strips. I'm sure I talked about that in a previous episode already. Now, looks quite nice, to be honest. I think, at least, and I'll put a picture of that in the show note, but it's not ideal because it has a lot of overshoot and undershoot, so at some point I'll probably have to redo this, or at least fix it. So, to be continued. And when making a homebrew device like this, maybe here's a tip for you. This device needs a 12 volt supply to operate, always. So what you can do is provide that 12 volts using a mains cord, power cord that will then have to go to an AC-DC converter. And first of all, you have to deal with mains voltages, so you have to think about safety more. You also probably have to add a switch to the device. And you probably also have to, at least if you're using a project box, a typical project box, which I did, you have to modify the front panel and the back panel because you want the mains voltage probably to come in at the back, and maybe you have to have a power inlet connector or something like that. So that sounds like a lot of work, and maybe because you don't need this box all the time, at least I don't need this box hardly ever, I guess. What I did instead was put two 4mm banana inputs on the front for the power supply for the box itself, and that's all. So when I want to use this thing, I take a lab power supply and two measurement leads and just connect the two together, and that's it. So maybe that's a tip for you, no idea. And one project I finished, I talked about it already last episode, is a LED spiky icicle light ball effect decoration. Essentially it's a 5cm diameter plastic Christmas ball with holes drilled in it, and plastic transparent icicles or spikes sticking out of those. And the spikes come from two existing Christmas decorations. They already had an LED effect, but was not very spectacular, so I decided to make my own improved version. So inside the center there's a AVR microcontroller with two 16-channel LED drivers on a small board, and with wires connected to the LEDs, and it takes 5 volt and about 500 milliamps max to display a nice effect. I'll put some pictures and video of that in the show notes. Now the software for this thing was a bit interesting because I wanted to avoid trigonometry and also floating point arithmetic, so we just used integer arithmetic and 8 bits values if possible, and if not possible 16 bits, and use some scaling and dividing and so on. So the software I do here is in C, mostly is in C for this kind of stuff, and I noticed that for me, if I haven't done C for a while, it's really easy to shoot yourself in the foot with this language. So for example, converting unsigned to signed and sign extension of values, and it's really easy to make a mistake if you don't know the C standard by heart. I'm sure some people do. Unfortunately, I do not. But now it works, so that's nice. And I'll probably hang it at the Hackalot hackerspace in Eindhoven when the virus stuff is gone and it's accessible again. The thing hangs from two metal wires, or at least that's the idea. Two metal wire stubs sticking out of the ball in the center, so you can hang it from the ceiling using two metal wires, one for plus and one for minus, one for ground. So maybe here's a tip for you: to connect two metal wires in an elegant way, let's say that, for stuff like this where it's suspended from a ceiling and shouldn't look too bulky. They have these thermal strips. I'm not sure what they call them in English. I think just thermal strips. You can buy them at any hardware store. It's really crude way to connect two wires together. You can cut with a scissors part of it as much as you need. You can fasten two wires together using a screwdriver and two screw sockets basically. I post a little picture of that in the show notes. You can take these apart and you have as many as you want, metal cylinders with screws to connect two wires together. So that may be interesting. And the last topic is a little bit fuzzy. It's about the relationship between yourself and your measurement gear, electronic measurement gear that you already own on your bench. So recently we had a problem here where we wanted to inspect glitches on a main circuit, and using a oscilloscope and a differential probe, in this case the Pintec DP25, we saw glitches that were much higher than expected. But the scope showed them, so it must be real, right? So afterwards we tested the probe itself, because I had never really done that. I just bought it and it should be okay, and never really tested it in isolation. So we used a used a function generator to look at the frequency response of the probe, and it was way off at some frequency, which may be the cause of the exaggerated glitch that we saw. So to make a long story short, the measurement equipment that you have, at least that I have here, I usually buy stuff and I believe it works. And maybe I should be a little bit more skeptical, because there was a time when I wanted to have the most accurate equipment, regardless of anything else. So I wanted to have a multimeter that was super accurate. But maybe it's more important that the measurement gear that you have is predictable and reliable. So predictable as in I should know the frequency response of this probe, and I should know the limits of all the gear I have and the flaws and the quirks. To name a few examples, your oscilloscope probe has a frequency response, so it starts performing worse from a certain frequency onwards. Your multimeter has true RMS multimeters have they measure the RMS voltage of arbitrary signals, for example a sine or a triangle wave or whatever. My multimeter can do that as well. They're not magic boxes, and the ability to measure the RMS voltage stops at some frequency, so maybe it's useful to know that. Also, some multimeters can record minimum and maximum values. Now, maybe in this time of self-isolation, if you have nothing else to do, it may be useful to see how short a pulse it can still record as a maximum and minimum. So hook a function generator on it and see how short you can make pulses so that the multimeter can still see them and record them as minimum and maximum. I recently also had a similar problem with a LED power supply, which had a little bit of overshoot. Normally it's not a problem if you turn it on, the output voltage is a little bit higher for a very short time than you set it to. In this case it was a microprocessor that couldn't really handle voltages higher than its absolute rated maximum. And it went into a weird mode that it didn't perform well, and it went to a weird lockup mode, something like that. So maybe it's useful to know that your LED power supply has overshoot in my case, or the ramp up voltage, what it looks like and how it behaves at power on and power off, and how fast it is, for example. Another thing is more digital stuff with a sample rate, for example your scope, and more specifically a logic analyzer, has a certain sample rate. Now the stuff I have here is pretty low budget. I have a logic analyzer as well, which has a sample rate, and at some point if you measure signals that are too fast, it just can't keep up, but it will not tell you that it can't keep up, so you will just see unreliable results. So maybe it's useful to know what the limits are of any equipment. That's what I'm trying to say. So what I'm also trying to say is, if you have nothing else to do in this period of viral unpleasantness, maybe take a look at your own measurement equipment and get a feel for the limits, and get a better relationship with your own measurement equipment. So that was all for now. For more information, links and previous episodes, visit podcast.cba.si. Stay tuned, thanks for listening, and goodbye.